Okay, so okay. So here we talk about the dipole in the electric field. So here it says, so the torque of an electric dipole of the dipole moment. So actually in this chapter previously, we have talked about what is a dipole. And here we try to place a dipole in the uniform E field to see what is the phenomenon here. Okay, so it says the torque of an electric dipole of dipole moment P when placed in an external E field, E is given by a cross product. Of course, here the mentioned external E field is a uniform E field generated by the infinitely large charge plate, as mentioned before. Okay, so here we have the E field pointing to the right side, and the magnitude is uniform. It's uniform over the whole space. So here it tells you that if you place the dipole in the external E field, which is uniform distributed, then there will be a torque acting on this dipole. So it will just like swinging back and forth like this, swinging this way and then swinging backward, and then just like an oscillator, just oscillating back and forth. Okay, so actually the torque will be P cross E, P cross E. And I suppose you have learned the cross product in the high school physics. So you may be able to know that the magnitude of the torque will be P times E times sine of theta. Theta is the angle between the vector P and the vector E. Okay, so for instance, in this figure, suppose initially the E field is pointing to the right side uniformly, and initially this is a dipole, this is the negative charge, this is the positive charge. So the magnitude of the P would be Q times D, the distance between these two charges. Okay, so if you still remember. And the direction of this P should be from the negative charge to the positive charge. So this is the angle of theta between the vector P and vector E. Okay, so this is the angle of theta. Okay, so in that sense, you know the magnitude of this vector, and the direction of this vector is like you need to use the right hand rule. So you use your forefinger pointing to the direction of vector P, which means that you use your forefinger pointing to the top right, and then you try to rotate to the E field, which is pointing to the right. So your thumb will pointing into the page. So your thumb will be pointing. Let me try. So this is the direction of the torque. The torque. Okay, just like this one. Okay, P is pointing to the top right, and then E field is pointing to the right side. So you use your forefinger pointing to this top right direction, and then you try to sweep to the vector E, and then your thumb will be pointing into the page. This cross means into the page, into the page. Okay, so maybe in starting from chapter 28, as we have learned the magnetic field or the magnetic field density, then we will frequently use the cross product. But in the electrostatic part, we seldom use the cross product. But here is the exception case. For the torque, we still need to use the cross product. And if the symbol is like this means out of the page. So this is like into the page, which is like an arrow shooting into the page. So you see the tail of the arrow. And then here, if this is out of the page, you see the head of the arrow. Okay. So we use this symbol to represent a vector out of the page. And this symbol with a cross means the vector is pointing into the page. Okay, so one more time. So if you use a forefinger pointing to this direction and then cross the E field, your thumb should pointing into the page, which is the same direction as this vector tau. Okay, so this is a talk. And then, yeah, and then next is the potential energy. The potential energy will be like negative P dot E. Okay, so this is a dot product. This is cross product. This is cross product. This is dot product. Okay, dot product. Okay, or inner product. Depends what you call it. Or inner product. Inner product. Okay, so for the inner product of two vectors, it turns out to be a scalar. So this is a scalar. For the cross product, the output should still be a vector. Should still be a vector. So this is a scalar, which means the potential energy. Okay, so it is a P dot E, and then with a negative sign. And then the magnitude should be the magnitude of P times the magnitude of E times the cosine theta. Theta is still this angle between the vector P and vector E. Okay, so yeah, so this is pretty much like this. And yeah, and actually we can have an analogy like if you have a curvature like this, and then you have a ball here. Suppose there is no fractional force, then the ball will roll down and then roll back like this, and then roll down again, and then rolling back and forth. So it is like there's some potential energy transfer into kinetic energy, and the kinetic energy transfer back to the potential energy, and then going back and forth. This is pretty much like this. If you place it initially at this position, then all of them will be potential energy, and then it will swing, for example, to this position, to here, then all the potential energy will become the angular momentum, or angular momentum. Angular momentum. Of course, it refers to some energy, some kinetic energy. Yeah, so, and then it will swing to this place, and all the kinetic energy will become potential energy again, and then going back. So it's just like an oscillator going back and forth, or like a single pendulum. Okay, so this is the energy. So if this theta is 0, theta is 0 degree, then u equals 0, because cosine, u should be negative PE, which means the minimum of the potential energy. For example, if you can see it here, so this is the minimum point of the potential energy. And for this system, we will usually define the middle point will be 0, which means that if it is 90 degree, if theta is 90 degree or plus or minus 90 degree, then u will be 0. So this u is larger than this one, because the potential energy, you need to define a reference potential. So we usually define the 90 degree to be 0 potential energy. Then then this expression will be better looking. Of course, you can also define the minimum is 0. Then you need to add PE here to make the expression of the potential energy not so elegant, but yeah, it's up to you. Just like for this one, for the potential energy, you can define, or this one is the minimum potential energy, and this one will be mgh, and this is mg times 0, which is 0, something like this. But of course, you can also define this one to be mgh, and this is mgh plus h, if this one is capital H. So yeah, so the potential energy, you need to consider the relative potential difference. So yeah, so here we simply talk about the phenomenon about placing a dipole in an uniform E field. So there will be torque and potential energy involved here. Okay, so if you have question, you can raise it in the chat room, and I will have two additional examples to finish off this chapter. So the first one is a clock face has negative point charge, negative Q2, negative 12Q, fixed at the position of the corresponding numerals. So the clock hands do not disturb the net field due to the point charges. So we can try to draw a clock face out. Oh, it's not like a circle enough. Yeah. Okay, so this is a circle, like a clock face. So for a clock face, it will be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like this. Okay, so it says on the numeral, we have the charge. For example, on 1, we have charge negative Q, and then here we have negative 2Q, so on and so forth. Up to here, we have a 12Q, for example. Here we have a negative 7Q, and then dot, dot, dot. Okay, so it asks you at what time does the hour hand points in the same direction as the electric field vector at the center of a diode. Okay, so here we need to determine the direction of the E field. So actually we can do some cancellation. For example, we can try to consider some symmetric. Yeah, actually it asks you the E field at the center of the diode, which means this is the center point. And we can actually do some cancellation. For example, if it is here, here it is 1, here it is 7. So we have a negative Q here and negative 7Q here. So in such a way, the negative Q charge will generate an E field pointing to this way. And yeah, so this is E1 due to the negative Q charge. And for the negative 7Q, it will generate a E field pointing to the opposite direction. And as much as we know, the E field should be like K times Q over R squared. So of course, this is a circle, a clock face should be a perfect circle. So for every charges, the R should be the same. So you can regard a K over R squared should be a constant for everything, and the only variable is Q. So here, as much as this is negative Q, this is 7Q. So part of them will be cancelled. So it turns out to be, ouch. It turns out to be like we only have, negative 6Q here, because one of the Q, you can regard them as cancel for the center point. Okay, so we only have 6Q here. We don't have a charge because this part is cancelled with that one, or correspond to one negative Q. Yeah, so similarly, when it is a 2 and 8, negative 2Q and negative 2Q will cancel. It turns out to be negative 6Q here, and so as 9, 10, 11, and 12. So all of them will have a negative 6Q, negative 6Q, negative 6Q, and negative 6Q. Okay, so we will have 6 vector pointing to the number 7 up to 12. And of course, the magnitude of them will be actually the same because R are different and all of the Q are the same. All of them are negative 6Q. So all of the magnitude here are have the same magnitude. And simply, we can determine the direction of the total E field. We should be pointing to this way, right in the middle of 9 o'clock and 10 o'clock, which means that at 9:30, the hour hand point in the same direction as the electric field vector. So this simple example lets you familiar with how to do the cancellation to simplify your calculation. Okay, so the next one is this. So suppose you have you design an apparatus. So its Chinese is 仪器, in which a uniform charge disk of radius r is to produce an electric field. The field magnitude is most important along the central perpendicular axis of the disk. Okay, so we only care about the vector at point P. So this is the axis of the plate. Okay, so so this point is at distance 2r from the disk. So you can consider r is the radius, and this distance is 2r. This is 2r, and of course this is r. This is 2r. Okay, so cost analysis suggests that you switch to a ring of the same outer radius r, but with the inner radius r/2. So this is r/2. So which means that you can save this part of material. Okay, assume that the ring will have the same surface charge density. The charge density doesn't change, which means the total charge will be reduced because the charge density will remain the same. And then you remove the inner part so that the total area reduced, so the total charge also reduced. Assume that the ring will have the same surface charge density as the original disk. If you switch to the ring, by what percentage will you decrease the E field magnitude at P? Okay, so we need to determine the E field, how much the E field reduces compared to this one. Okay, so this one is quite simple, as we already know an equation of E equals sigma over 2 epsilon naught 1 minus z over square root of z squared plus r squared. So we have derived this equation for a circular plate, circular disk with charges. Okay, so we can make use of this one. Even though this is not a solid disk, we have a hollow part in the middle, but still we can use this formula to redefine the E field for this one, for this structure. Okay, so First of all, we may call it this is A, this is B, this is A, this is B. So the E field here we consider it is E sub A, E sub A, and this is E sub B. Okay, or maybe we can just call yeah, not necessarily this is EB. Yeah. Okay, so maybe first we try to calculate EA, which means that the E field generated by the whole disk. Okay, so here, so we simply substitute the values. So sigma over 2 epsilon naught, and then times 1 minus. Here, this is Z equals 2R. So we have a 2R over square root of 2R quantity square plus R square, like this. Okay, so all the R can be cancelled, and we can have sigma over 2 epsilon naught, and then 1 minus 2 over square root of 5, like this. And then here, we try to calculate the E hollow part, which means that the E field generated by this part will be E hollow. Okay. So if we subtract the E field generated by the whole disk by this hollow part, then it is the E field generated by the ring. And actually, we don't really need to calculate the E field generated by the ring, because we would like to calculate what percentage will you decrease the E field magnitude at P, which means that we try to calculate the E field generated by the hollow part, and then divide by this one will be the percentage you decrease. So here we try to calculate the hollow part generated E field. So it is a sigma over 2 epsilon naught, and then times 1 minus, still this is Z equals 2R. So we have 2R here over square root of 2R quantity square. But here, this is not R square anymore, because for the hollow part, the radius is R over 2 rather than R. So this one should be R over 2 quantity square. Okay, like this. So actually this one will be sigma over 2 epsilon naught, and then it will be 1 minus 4 over square root of 7. Okay, so so here we would like to calculate E hollow over EA will be, okay, so this one, this sigma over 2 epsilon naught cancel each other. So it turns out to be 1 minus 4 over square root of 7, or over 1 minus 2 over square root of 5. And of course, we can just multiply by 100%. So this one will be 28.3%. 28.3% will be the answer to this question. Okay, so of course, in order to save the material, save the cost, you reduce part of the material so that you save the cost. But in this case, if you just keep the charge density, then you will generate a smaller E field at point P. But yeah. Okay, so I think that's it for this chapter.